So we have been discussing about process management because the previous day we finished the file handling. So after process management, you have the uh, memory management. So then your operating system topic is, so this is one of the smallest topic. And always you get question, of course, few MCQ questions and most of the time structured essay question, okay? So remember, process is running program. Operating system manage programs in two different way. One step is operating system help install, uninstall, upgrade software. So all your installation, uninstallation, upgrades are under the control of the operating system. So that is one place where operating system come into the play. The second thing, and what we are more interested is, the programs are run by under the control of the operating system. A running program or running software is called process. Okay, running program or running software is called a process. Right. So what is a process? Process is a running program. Right. So programs are run under the control of the operating system. So how does program can start it? Of course, a user can start a program. For example, I just about 2 minutes ago, I started the Zoom program. I started this pen program. So then the program can be started as a scheduled task. So you schedule a task in the operating system, and when that particular time comes, it is getting executed. And also one program can start another program. Rather, the better term is one process can start a sub-process, like starting another tab in your browser. So that is how things get started. Okay. And how does program get terminated? We did these things last class also. That is, naturally the program has completed. So if it is some sort of a calculation or something, now maybe your program has terminated, naturally that completed the task and the program will be terminated. Or the user has decided to exit. For example, maybe after around 6, I will exit the Zoom program. Okay. So third one is, due to some issues or conflicting situations, the operating system can terminate a program. Maybe OS cannot further run this because of the error, or it is running out of resources, and so on. Okay. Right. So can't programs run on its own? Of course, if your computer is a very simple device which does only one task at a time, or maybe one task and single user, yes, then of course you don't need an operating system to run programs. But modern operating computers are multitasking, multi-user. Multiple users can log into the system at the same time. And not only that, a single user can run multiple programs. So therefore, there can be resource conflicts, okay, and so on. So therefore, you need operating system to manage or run these processes or running programs. So that is the idea. Okay, right. So remember, modern computers are multi-user and multitasking. It's no longer single user, single tasking, like the DOS operating system era, or Apple Mac, or Apple PC DOS, or Microsoft DOS. Modern computers are multi-user, multitasking. So that means multiple users can log into the system at the same time, and a single user can run multiple programs at the same time. So therefore, at a time, sometimes hundreds of programs are run. So how does computer or operating system do this? So there are different possibilities. So the approach that we discussed is under operating system is context switching. Your operating system give time slots to different running programs. In theory, at a time only one program is running, but frequently the different time slots are given to different processors so that we feel like multiple programs are running. So that happens even when you have a very simple processor, single processor, single threaded, single core, single processor. Still, users can feel like multiple programs are running because of this context switching. Right? So even in modern computers, we heavily use this. Of course, in modern computers, there are some other approaches as well, but it doesn't mean that context switching is not used. Context switching is the main approach. But these days, we have the multiprocessors. So not one processor, multiple processors in your motherboard. Of course, our normal laptop, smartphones, we don't have multiprocessor. So those are single processor. But there are special servers which has multiple processors. So then different programs can be run by different processors at the same time. Maybe program A or process A is run by processor 1, program 3 or the process 3 is run by processor 2 and so on. Or maybe process 3 and process 5 is run by program 2 by context switching. Process 1, process 4 and process 6 run by processor 1 using context switching. So multiprocessors. Another approach is single processor multi-core. Single processor. Physically, you don't have 2 or 3 processors, just one processor. But it behave like multiple logical processors. Physically one processor, but it behave like multiple logical processors. So we call it multi-core. For example, this laptop that I'm right now using is a multi-core processor. Okay, multi-core processor. It's a dual core processor. 2 cores are there in my single processor. It's not multi-processor, multi-core. Okay. Another approach is multi-threading. So thread is independently running program. So your operating system can run multiple threads. Okay. Again by context switching. So therefore your program can have multiple threads as well, like sub-programs. So the main approach is context switching. So that is always be used. But to supplement that, you can have multiprocessors, multi-cores, multi-threading, and so on. And these are, of course, hardware support is needed. Okay. Right. So that is how the multitasking, multi-use multitasking happening in computer. Right. As I told you, we are more interested in context switching because this is the main task that mentioned in your syllabus. Okay. Related to operating system because operating system has a big role to play here. So context switching means, let's assume we have one processor, one core, one thread. Okay. Still, multiple processors can be run, but in reality, at a time only one process is running. Only thing is, time slots are given. Maybe this is process 1, then process 2 is given the attention. Process 3 is given attention, again attention given to process 1, maybe again process 3, now process 2. So likewise, so therefore we feel like each and every process has a progress. But in reality, at a time only one process is running. If you draw a line, vertical line, at a time only one process is running. But over the period, we feel like this is also proceeding, this is also proceeding, and so on. So that is called context switching. But if you have multiple processors or multi-cores, yes, so then similar thing is happening in another core, another processor. But inside that, again, context switching happening. Okay. So processor periodically allocates small time slots for each running process until the process terminates. And those time slots are extremely small, right? Extremely small in milliseconds. So therefore, we feel it like all the processes are happening at the same time. And operating system has strategies to allocate to those time slots. It's 100% operating systems. One of the main tasks of the operating system. Right. So this is the most important diagram for your exam when it comes to process management. We start discussing this last time, but in the middle halfway, we just I had to stop the class because my battery went dead. Right. So when you run a program, say you just click on that program or the scheduled task has started. So that program is initially in the or a program or the running process is initially in the new state. We say that the process is in the new state. New state means you just started it, still it has not given the attention by the operating system. Operating systems has not given the attention to that. So that is why sometimes when you run a program, there's an initial delay. So the reason is maybe operating system is so busy doing other tasks because operating system is one of the busiest program doing thousands of things, not hundreds of things, thousands of, because running program is not the only thing for the operating system. It has to run, manage hardware, files, security. Right? While doing all those things, it has to run programs, manage running programs. Of course, the programs are run by the processor, but operating system need to manage. So therefore, initially there will be a small delay. So during that period, we say that the program or the process is in the new state. Still, the operating systems has not given attention to that process because maybe it is giving attention to some other process. So once operating system give attention, uh, we say that that particular process is now in the ready state. Basically, operating system has taken that program to a waiting queue, ready queue. Earlier, it was not even in the queue in the new state, but now you are in the queue. You are in the queue doesn't mean your program is getting run. You are in the waiting queue with other processors. So then operating system time to time give time slots. So give attention to those processors in the ready state. Right. So therefore, maybe the program that we are interested may also get that attention or the time slot. So when that particular program or process which was in the ready state got the attention or the current attention, we say that that particular process is now in the running state. So it is now being processed by the processor. It's just a few milliseconds. After the time slot is over, if the program is not finished, most of the time it is not going to finish in one particular time slot. So then it has to go back to the ready state. So this is called admit, this is called dispatch. And after the time slot is over, it has to get back to the ready state. So we say timeout. Why? Because operating system want to give attention to a different another waiting or ready process. So therefore, your process need to go into the ready state, ready queue. So again, when your time slot comes, that process again goes to the running state and again getting back to the ready state. It keep happening. Maybe few times, sometimes even hundreds of times. If it is a long program, long process, time consuming process. And of course, once your program is fully processed, it has done its task, or user has exit, or operating system decide to terminate it, then it goes to the completed state. Okay, or exit state. We say that the process has released to the exit state. So it can happen when it is in the running state. Okay, so rather than going back to the ready state after timeout, it can go to the release state because the program has finished its task or the timeout. Okay, timeout in the sense, sorry, not the timeout. The program has finished its task or the user has closed it, or due to some error, program has been terminated. So you are going to the exit state. But before coming to the exit state, there will be many times it goes to the ready to running and running to ready together with other processes. Okay. So now we have discussed 4 states: new, ready, running, exit. Okay. Right. So then another thing can happen. That is, while your process or running program is in the running state, that is, it is now getting run. So remember, a program is not always doing processing. A software, of course, software is supposed to do processing, but it doesn't mean that all the time it is doing processing. So there are situations it is waiting for the user to input some data or accept some message or something. Okay, cancel. So those things are frequent, right? For example, if you have ever seen an ATM machine, how it works, there are few times the ATM machine wait for the user to maybe enter the PIN number, insert the card, select a menu option, enter a value, and so on. So therefore, in that kind of a situation where it is waiting for user to do something, what happens is while running, it detected that, okay, now the user need to do something. So in that kind of a situation, rather than taking back to the ready state, the operating system take that process to the block state. So why do we call it block state? Because it is blocked for user action. Until user action is done, no point taking it back to the ready state. So therefore, rather than putting it to the ready state, your operating system can take it to the block state. Okay. It's waiting for a user event or user action. Okay. And while it is in the block state, it can never come back to the running state directly. Say while it is in the block state, after a few seconds, the user has given attention. Maybe user has click on the OK button or cancel button or entered a particular value and submit. Now, remember, until that time, even when the user is doing some interactions, your process is in the block state now. Because until user actions are finished, there's nothing to be run. But once the user action is finished, it can go from block state to the ready state. So that means the user event has completed. Remember, until during that period, it was in the block state. Now it is getting to the ready state again. So remember, it can never ever go from block to the running. Those are the important things. So while it is in the block state, when the user event happens or finish, it can only go to the ready state. Right, ready state. So ready state means you are again getting to that queue, waiting queue. And again, when the operating system give a time slot, because while it is in the block state, operating system does not give it that process time slots because no point. But once it getting back to the ready state, now it is again a candidate for time slots. It doesn't mean that immediately you get the attention. No, you are now in that queue again. And when you are in the queue, of course, yes, you will get the attention after some time. And again, it can go to dispatch timeout, dispatch timeout. And if there's another user interaction, it can again go to the block state, and after user interaction, again go into the ready state, again dispatch and timeout, and maybe after everything is done or terminated, it goes to the exit. Okay, right. So anything not clear up to this point? Up to this point. So we have discussed 5 states now. New, ready, running, exit, blocked. So we have 2 more states to discuss. So this is the simple way we can look at it. Right? We can look at the process, how the processing is happening. But unfortunately or fortunately, I don't know, this diagram is not this simple, because operating system is doing something called, use something called virtual memory. Remember, memory management is our next topic anyway. So because operating system does use something called virtual memory, this become even more complicated. So this itself is somewhat complicated, but it's more complicated than this because of your computer use something called virtual memory. Right? What is mean by virtual memory? You know that in the computer there's a storage hierarchy. You have the registries in the processor to keep the instructions and currently running instruction and intermediate results. So then you have the RAM or main memory. Of course, above that, if you want, you can think of cache memory as well, but just ignore the cache memory for the time being. And then you have the secondary storage. And then tertiary storage, like backup storage, pen drives and external hard disks. And this RAM is very important. This RAM is very important because your processor take content and write content to the RAM rather than directly working with your secondary storage like SSD and hard disk. So your processor prefer to work with RAM rather than directly work with secondary storage like hard disk and so on. So the reason is in the RAM you keep data and programs in electronic format, 1-0 level. And also accessing electrical thing is faster. These are mainly if it is a hard disk, magnetism, some mechanical things, and so on. So those are inherently slower. Okay. But the issue is there are frequently some times where the RAM is not enough. Maybe you have 4 GB, but currently demand about 6 GB. Maybe you have 8 GB, but it demands about 12 GB for the RAM. Okay. So in that kind of situation, your operating system does a trick. That is, it can borrow part of your secondary storage, maybe SSD or hard disk, maybe few gigabytes, and consider it as part of the memory or RAM. Your operating system view it as part of the memory, but in reality, it is not part of the memory. So we just borrow that to help managing our data and programs in the memory. So this borrowed portion from the secondary storage is called virtual memory. It's not real memory, but it acts like something like the extension to the memory. That is why we say virtual memory. But in reality, this is virtual memory, because if in reality it is in your secondary storage, hard disk or SSD. Maybe 4 GB in the real memory, 1 GB is in the virtual memory. Right? So this is your real physical hardware memory, maybe 4 GB, but 1 GB is taken from the virtual memory or your secondary storage. And this is called virtual memory, this part. borrowed from the secondary storage. Altogether, we can call it logical memory. Sometimes logical memory is also called virtual memory, but the better term is virtual memory is basically that borrowed part from your secondary storage. But sometimes the entire thing is also called virtual memory. But the better term is this is physical memory, this is virtual memory, and altogether we can call it logical memory. So how does your operating system use this virtual memory? When you are running out of, or when your system is running out of memory, which often happen, what it does is it copy some content from the memory to the secondary storage or the virtual memory or the logical storage, logical memory. Okay. And later it can take it back to the memory. So usually, though maybe you are running about 10 programs right now, but some of the programs are idling, while some other programs are really running. So operating system can take memory portions of these idling processes and write it to the virtual memory or the portion reserved from your hard disk SSD. So that freed physical memory can be used for some other program to run. Okay. But remember, when the content is taken to the virtual memory or your secondary storage, it is no longer directly accessed by your processor. Okay. So that means that memory portion is taken to the secondary storage or your virtual memory. Of course, it is considered as part of the memory, but the operating system, the processor cannot access content in the virtual memory. So therefore, you can't run a particular program or process while part of your content are in the virtual memory. So then we say that that process is in the suspended state. Suspended means the entire process or part of the process, the memory related to that process is in virtual memory or secondary storage. So how can it go to the ready or suspended? Both are the same, just two names we use. Your process can go to the suspended while it is in the ready state. It was in the queue to be run, but before it got the time slot, operating system has decided to take a particular memory part to the virtual memory, and that memory part belong to maybe that particular process. So then we say that the process has changed to the ready or suspended state from ready state. So ready or suspended means that memory related to that program is in the secondary storage. Okay. And again, when that memory issue is resolved or your operating system decide to take that back to the main memory, then it goes from ready or suspended to ready again. Okay. So it can happen many times as well during the execution. So that happened while your process was in the ready state, ready queue. Same thing can happen while your process is in the block state. Your process was waiting for the use action. While it is waiting for that use action, the operating system has decided to take part of the memory to the secondary storage. Part of the memory will related to this process. So then we say that it moves from block state to the ready suspended. Right. Block state, it has changed to the block suspended or block core suspended. Now after some times, assume that memory usage is lower. So therefore, again, operating system has taken that memory dump in the secondary storage back to the main memory. Remember, but if say it happened while it was in the ready state. Sorry, while it was in the block state. That means it was waiting for the user actions. But because of the memory issue, it has taken to the block suspended state. So this is ready suspended. While it was in the ready, came to the suspended. This is block suspended. While it was in the block state, it was taken to the suspended. Now while it was in the block suspended, two things can happen. One thing is that memory issue is resolved. But still, the user has not responded to the user event. But the memory issue is resolved, so therefore the operating system has taken it back to the main memory. So then it goes from block suspended to the block again. And again waiting for the user actions to get into the ready. The second possibility is while it was in the ready suspended, there is no user input requirement. While it was waiting for the execution, you put it into the ready suspended because you take part of the memory to the secondary storage. Now again, when the memory issue is over, it can come back to the ready state. Right? So that means again it is in the main memory. Okay. So there's another possibility. So that means it can go to the suspended and come back to the blocked. That means still the user has not responded, but the memory issue has been resolved. Okay. So do we have another possibility? Can your process go from block suspended to ready suspended? So the answer is yes. How? Now remember, your process came to block suspended because it is waiting for the user input. At the same time, it is now in the virtual memory. If the user input virtual memory issue is resolved, it can go back to the block. But maybe still the user attention is not given. Still it is waiting for the user input. But memory issue has been resolved. And now it is back in the main memory, main RAM, not in the hard disk. So then it goes from block suspended to ready suspended. Okay. And maybe while it is in this state, now the memory issue is resolved. Now here the user attention is given, but the memory issue is not resolved. That is why it goes from block suspended to ready suspended. But maybe now the memory issue is resolved. So then it can come back to the ready state. And of course, when it get the time slot, it goes to the running, coming back to ready, go to the running, coming back to ready. Maybe while it is in the running again, it can come back to block. Maybe block to ready or block to block suspended, then come back to block and ready, or block suspended, ready suspended, then come back to ready. So those are all possibilities. And this is a very important diagram which explain what are the possible states process can go until it get into the exit state. Always it start in the new state, always it ends in the exit state. And these are possibilities. This is super important for exam. Okay. Any questions? Because this is super. If you understand this, sometimes there is a full question or maybe at least sub part in the structured paper. Of course, there can be one or two MCQ question as well. Right, I already explained these states: new state, ready state, running state, exit state, block state, block suspended states, ready suspended state. Okay. Right. Any questions? Because this is a lot of students really misunderstand this, unfortunately. So they can't explain exactly from which state it goes to the next state and what is the reason. Right. Yes, it's a fairly complicated activity, but this can effectively make us feeling like multiple programs are running. But in reality, only one process is running at a time. Okay. And these state changes can happen in a split of a second. Right. In order to do these tasks, taking one step, a process from one state to the other, and get the collaboration from the processor. The processor has a component called process scheduler. It is part of the processor. Its main task is doing the scheduling, giving each and every process a fair chance to run while doing all the other management like hardware. Okay. So the process scheduler is a sort of a subcomponent of the operating system. Its task is to provide a fair opportunity for each process or fair amount of time slots for each and every running process. So usually try to give equal opportunity, but in reality, there are some processes operating system will identify those are high priority. Some other processes are relatively low priority. So then high priority processes will be given more attention, more time slots. Low priority processes are given small time slots. That we can override as user by changing the priority of your process. Okay. So if you want to look at how these things happen, you go to if you are having a Windows operating system, say task manager, right click and go to the task manager. Then go to the process. So these are the running programs or the processors right now. You can see in my computer, at least there must be more than 100 processors. And most of these processors are related to the OS tasks. But some of the others are related to the programs, like in this case, Chrome, Firefox, Epic Pen is running, Task Manager itself is running, WhatsApp is running because WhatsApp is here. Okay. And you can see how much of a CPU is allocated right now, how much memory, and so on. And here you can, right, so these are the startup process, automatically started the programming. So this is the running program, so services. You can see a lot of programs are running, but though you can see that a lot of programs are running, actually at a time only one program is running, one or two program. And because the context is switched very fast, we feel like a lot of programs are running. Okay. And if you want to change the priority, you can right click and set priority. You can see almost every process has a normal priority. You can give high priority. So that means operating system will give more time slot to that one. But there's no guarantee. But in general, operating system try to give high priority process little bit more time slots. Okay. So therefore, go to the task manager and have a look at those things. If you have any doubts, you can ask. Okay. About these processes and so on. So we can identify, oh yes, in general, it's a process scheduler, right? We call it the part of that operating system subprograms. We can call it a process scheduler. But in reality, you can look at it as three process schedulers. Right? Not just one process scheduler. You can subdivide your process scheduler into three process schedulers. long-term scheduler, short-term scheduler, and medium-term scheduler. So the long-term scheduler's task is admit process to the ready state. Remember, initially, your program is in the new state. So which scheduler decide when to take a program from new state to the ready state or put it into the processor queue? That is done by, right? So this task is done by one particular scheduler called long-term scheduler. Manage admitting process. So long-term scheduler does the admitting from new to waiting or ready. So that is done by long-term scheduler. Then short-term scheduler is the one that manage going from ready to running and so forth. Okay. So basically this is done by long-term scheduler and this is done by short-term scheduler. Okay. And then there's a need to take it to the suspended and variation of suspended and so on. Those things are pretty much done by mid-term scheduler. There are 3 schedulers taking care of 3 different things. Right? Long-term scheduler, short-term scheduler, and medium-term scheduler. So this is long-term scheduler that take from new to the ready. Short-term scheduler is taking your ready to the running and running to the ready. And medium-term scheduler is the one that is taking to the suspended and getting back to the back from suspended and so on. Okay. Right. So remember when it comes to running a program, the main thing is it comes to the ready state and the running state. Ready state, running state. Of course, it can go to suspended, block suspended, and so on. But this is the main thing. Okay. So for example, when the program's time slot is over, then it has to go back to the ready state. And remember again, after some times, it has to come back to the running state and run a part of the process. So this is necessary because we want to give the feeling that all the programs are running. But at the same time, this is overhead as well. Right? So think of, say you have 5 tasks to do in the day. Right? So you have 5 tasks. Task number X, let's say task A, B, C, D, and E. So one possibility is you finish the A task and then go to B task and then go to C task, D task, and E task. Maybe the E task is done in the evening. Whereas A task, you did it in the early morning. But the expectation is that all the tasks must proceed. So then what you have to do? You do bit of task A, then bit of task B, bit of task C, bit of task D, bit of task E, maybe within the first 15 minutes. So then you need to resume the task A from where you stopped. So in order to resume from where you stopped, you need to save, when you stop this A task to start the B, you need to save what is the current status, right? Because you need to start from that point. And same thing you need to do each time you stop, each time you stop a particular task temporarily, you need to save the current state. So that when you get the time slot again, you can resume from there. So what is meant by current state? What is the last subtask or the instruction you have been executing? You just executed. What are the variables values right now? Because you have been working on some calculations. What are the current values of the variables? All those things you need to save, because uh, again, your processor is going to use for the second task, because your processor registries and everything is going to be initialized with a different task. Then again, different task, again, different task. And again, you need to initialize the registries and everything with the values that you stopped last for the task A. Okay. So this saving these, what is the current instruction, what are the variables, values, and so on. And sometimes you may have opened a file and so on. So this is called, so you need to save it, right? Save it. The operating system need to save it in a particular data structure, and we call it process control block, PCB. So every time you take running process to the ready state, you need to write to the process control block and then take it back to the ready, waiting state or the ready state. And the first thing you do when it is going back to the running state is read the previous PCB and initialize it, initialize the task. Okay, so this is called process control block. Process control block. It's a data structure used to keep the information needed to manage the context switching. Stop it and resume it. When you stop, you write the PCB. When you resume, you read the PCB of that particular process. Each process has one PCB. Each process, each running program. Okay. So exact structure depends on the operating system. So different operating systems like Windows, Mac, Linux, they use slightly different PCBs because those are independently developed operating system. But this is just high level. What are the, in general, what are the things that the PCB will have? Of course, the process number. Otherwise, you can't identify for which process which, because you need to keep track of multiple PCBs. So therefore, each PCB can be identified using the process number. So then we know that this PCB is for this process. In the process state, remember when the PCB is written, maybe it is in the ready state, but there is a possibility when it is goes taken to the suspended state, okay, block state. So whatever the state must be mentioned in the PCB. Of course, the process number. Program counter means what is the currently executing instruction number. Maybe it has thousands of instruction. Maybe now you are in the 850th instruction. Because next you need to start from the 851. No need to start from the beginning again, because you have finished up to this point. Program count. Then the registry values. Those are the temporary values of the variables at the suspension of that task. And of course, list of open files. If that particular process has started, open some files, because when it is given the attention back, again, you need to start open these files. So that is why I'm telling you that this context switching has a overhead also. But we have no other option to go for the context switching, though it has overhead. Okay. And all these details are written to something called process control block. So you must know the purpose of process control block and what are the major contents of process control block, like process number, program counter, process status, registry values, list of open files, and so on. Okay. If it is not clear, you can ask, right? I can explain it again. Especially, you must know the reason for having PCB. So basically, it has the scheduling information, memory information, input output status, and so on, right? But this is what basically you need to understand. So forget about this slide for you guys. Just remember these are important for you. Right. So this is not directly related to your syllabus, but we never know, right? You know that A-level ICT is super competitive. So they can ask few advanced questions little bit beyond your syllabus. So therefore I have added this slide and another slide for that. So this is what classification of processors or classification of running programs. So we can classify programs or processors as CPU bound processors and IO bound processors. It's a very simple classification. CPU bound processors means that process or that program heavily involve processing. So it need heavy attention of processor or arithmetic and logic unit. So those are process oriented. Heavy calculations and so on are needed. So those are called CPU bound. CPU bound means you need a lot of attention from the CPU or the ALU. But there are some other programs which are most of the time waiting for the user interactions. Bit of processing, again use interaction. Bit of processing, again use interaction. And of course, you know that the user interaction, users are slow. Users are slow to interact. So therefore, these programs need less attention from the processor. It is most of the time in block state. Considerable amount of time, those processors are in the block state, waiting for user responses. And we call them IO bound processors. Right? CPU bound processors, IO bound processors. For example, at the end of this session, so remember, I always record this session. So after this session is terminated, another window opens and it starts processing the video recording. It happened for another 5 minutes. For 2 hour session, it take about 5 to 10 minutes to process it. That is heavily CPU bound process. So during that period, even I can feel my computers getting heated, heavily process oriented. Process usage goes to something like 100%. Okay. But if I'm doing some word processing and so on, so most of the time your processor is idling. So I'm just typing something, maybe doing some formatting. So in between, lot of idle time. So those are pretty much IO bound processors, whereas graphic processing, some calculations, scientific calculations, those are heavily CPU bound processors. Okay. And so that is one classification. So the next classification is also very, very important for your exam. That is preemptive processors versus non-preemptive. It's actually preemptive context switching versus non-preemptive context switching. Right? So preemptive means fixed time slots are allocated to each process. So if you have 10 processors, each process is given sort of a fixed time slot, but it can be slightly different depending on the priority. But usually each process is given, say process A is always given 10 milliseconds. Maybe process B is always given 20 milliseconds. But again, it get a 20 milliseconds. Again, it get a 20 milliseconds in general. So whatever fixed time slot. But that value can change depending on the priority. But for a particular process, it is sort of a fix. We call it preemptive scheduling. So the idea of that fixed time slot is give each process sort of a opportunity. So that is why after the time slot is over, you need to get back to ready state and allow other process to run. So this is good for democratic manner, right? So each process get a reasonable good attention in preemptive process scheduling. So the other approach is non-preemptive scheduling. In non-preemptive scheduling, when when a particular process start, okay, it completes its task or it reaches the waiting state. So it is not a small time slot. So when a process is taken to the running state, usually it is given time to finish it. Or if it get into the waiting state that the user interaction is required, so then also it can be taken back to the ready state back. But usually that operating system allow it to finish it. So those are called non-preemptive scheduling because there are some requirements you need to, when you start something, you need to finish it without taking breaks, like real-time processing. So those are non-preemptive scheduling. But most of the time, more than 95% of the time, in reality, what we have is preemptive scheduling. Fixed time slots are given. Not you are given the attention and to finish it. Because when one program is taking a lot of time to finish, most of the other programs are sort of a halt. So the users might feel like it's only one program is running. So that is the disadvantage of non-preemptive scheduling. So practically most of the time it is preemptive, but there can be even preemptive, non-preemptive mixture. So you can give a very high priority to a program so that it get the non-preemptive attention. Maybe other programs get the preemptive attention. So you must know you must know what is preemptive, not what is non-preemptive. Preemptive means time slots are given. Non-preemptive means when a process is given the attention, usually it can finish it or until it goes to the block state. Okay. Any questions about preemptive versus non-preemptive? Because this is super, super important thing. Super important thing. Right. So I told you that context switching is one solution and the most important solution of multitasking, multi-user multitasking. But these days, of course, until about 1980s, context switching was the only solution because until that time, we had only single processor, no multiple processors, no multiple cores, no multiple threading, just single processor. So at that time, the only solution was context switching. But now, with context switching, we have some other solutions also. But other solutions have not replaced the context switching, rather enhance the context switching. So what are those solutions? Go for multiprocessor, multi-core, multi-threading, or mixture of those. I already explained you what is multiprocessor is. So multiprocessor means your motherboard has multiple processor chips. So usually those motherboards have two slots to fix two processors, so 2 or 3 or 4. Right? So those are called multiprocessor. So very high-end computers like some servers, you will find multiprocessor. Physically, multiple processor chips are used and they are connected to the RAM separately. And different operating system can allocate some programs to processor 1, some programs or some processors to processor 2. So therefore, there's overall high efficiency in multiprocessor environment. But of course, the cost goes up. For general purpose tasks like our day-to-day work, usually we don't need multiprocessors. But for very high processor intensive things like servers, we can go for multiprocessors. So the next thing is multi-core. So there's a big difference between multiprocessor and multi-core. Multiprocessor means more than one processor chips. Separate chips are fixed to the motherboard. Multi-core means it is one processor, just one chip, one physical processor. But inside that, there are multiple processors, right? We call them multi-cores, multi-cores. But those are in the same chip. So this is very popular these days. For example, this particular laptop is dual core. It is not multi-processor, but it is a dual core. Okay, multi-core. And each core can act like multiple logical processors as well. So forget about that. Just remember, for example, in my case, if I go to my task manager, and go to the CPU, you can see, I don't know whether you can see it. Clearly, I can see. It says, sorry, my one is not dual core, quad core. 4 cores are there. Right? 4 cores are there. That means single chip, but my single processor act as 4 cores. And you can see that 4 cores, 8 logical processors. That means each core is considered by operating system as logically as 2 processors, 2 cores. So therefore it's single chip, single processor, but inside it has 4 cores, and each core is viewed as a logic 2 cores, processors. So therefore altogether operating system see it as 8 logical processors. But it is single processor, 4 cores, 8 logical processors. You can see 4 cores, 8 logical processors. And of course, it is a single processor. Single processor, 4 cores, 8 logical processors. In my case, in my computer, my laptop. Okay. So that is to optimize the usage. Get the maximum from your processor. Get the maximum from your processor. Right. So now you must understand what is mean by multiprocessor, multi-core. So then you have the concept of multi-threading also. So threads are sort of a sub-programs. For example, your operating system can look at one program as multiple threads or multiple sub-processors. That is again to give them more opportunities to quickly execute. For example, if I take not every program or process has multi-threading, but if you take something like, say, Firefox, you can see I have about 3 tabs here. So each tab is usually a one thread. Oh, it looks like my operating system look at it as not just one program or one process. It look at it as 3 sub-processors. So sometimes even 4, 5 sub-processors if there are some background download and so on. So you can see that also if you go to the task manager and processors, and if you expand this, you can see there are so many sub-processors. So one sub-process for each tab and some other sub-process for any other background task. But that is not always the case. For example, Zoom, look at it as 4 sub-processors. Edge, look at it as again large number of sub-processors. Okay. So likewise, you can see that here, of course, I have 3 PowerPoint presentations. Each PowerPoint presentation is taken it as 3 sub-processors or threads. Okay. So all these concepts are used to have a very efficient execution of your programs, right? What are the things we use? Context switching, multiprocessor, multi-core, multi-threading. Okay, multi-threading. And of course, there's a concept called multiple logical process, which we did not cover. An operating system need to handle all these things. Right? So that is why operating system is one of the most complicated software in the world. That is why we have only few operating systems in the world. Windows, Linux, Mac, Android, and all those are US based. So that remember about 2-3 years ago, there was a big demand for Huawei smartphones. Huawei smartphones. But USA decided, okay, Android is not allowed on Huawei smartphones. And ask Huawei people, don't use Android. If you want, you can have your own operating system. And within few months, Huawei is out of the market because they can't make their own operating system. They can make phones, but they can't make the operating system because operating systems are super complicated. One of the most complicated software man has ever made. Okay. And also to further enhance the processing, there are some other concepts like parallel computing, distributed computing. Of course, parallel computing means you have multiple processors. Multiple processors. Distributed computing means the processing is not done by one machine with the collaboration of multiple separated machines in the network. So part of the processing is happening in one machine, another processing is happening in another machine, and so on. Your processing is distributed among computers. So, this is done when we are processing heavily complicated logic, heavily process-oriented things. Sometimes with one computer, it might take days. Maybe in a distributed computing, we can do it in few hours because each computer is contributing. So that is called distributed computing. Having multiple processors is called parallel computing. Right. So that's it about the process management by operating system. Okay. So any questions? Because we can do some past paper questions after the memory management. Now we have done the 2/3 of your operating system topic. File handling, of course, we did the introduction, then the file handling and the process handling. Any questions on process handling? Right. So then we can move on to the memory handling or memory management. And this is the hardest topic. I'm not saying that the process management is difficult, but you should be able to understand process management. But memory management is the most popular topic for the examiner because examiner can give you some calculations. And you can do those calculations only if you have perfectly understood the concept. Perfectly. If you have even a slightest doubt, very difficult to do those questions because those are calculations in the structured paper. Okay. So remember, computer manage hardware. Earlier we discussed computer manage files, then computer manage software or processors. Now we are into the computer managing hardware. And previous topic is partly related to computer managing hardware as well, because when it comes to process management, how we allow programs to be executed by the processor. So therefore, it's part of the managing process as well. And of course, it manage each and every component of your computer, like keyboard, mouse, and everything, printers. But we are only interested in this topic about how computer manage memory. Right? How computer manage memory, because memory is a very important aspect. Remember, we discussed in the process management also, when the computer is running out of memory, it borrow part of the secondary storage as a virtual memory. And therefore, your process diagram has had extra states, suspended state, block suspended, and so on, ready suspended. So that is because the memory management is not that simple. It even borrow secondary storage, part of the secondary storage as an extension to memory. Okay. So first of all, why do we need memory? Because accessing memory is faster than accessing the secondary storage. Memory is, in the memory you keep data in electrical charges. In secondary storage, it is slightly different. Of course, in SSD, you keep it in electrical charges, but it is not as efficient as accessing your RAM. And also, you know that in hard disk, it is stored as using magnetism, which is very slow. That is why we say hard disk, use of hard disk is very slow compared to SSD. Right, we discussed bit of memory or the memory management as part of the computer architecture topic. So the big picture you have. Okay. So therefore, we are more interested in memory address translation process here. But before moving to the memory address translation process, we need to do a little bit of refreshing of what we have already discussed under computer architecture. Okay, introduction to computer. So remember, storage is a hierarchy. You have the registries, cache, L1, L2, L3, then the memory, secondary storage, tertiary storage. It's a hierarchy. And memory is part of that storage hierarchy. And from the other side, you have the ROM also. And we will look at the purpose of computer memory and what is mean by virtual memory. I told you it can borrow part of the secondary storage as extension to the memory. And we'll look at very briefly what is NDNS and byte ordering. Then we will look at what is physical memory address and what is logical memory address. And of course, our ultimate topic is memory address translation. So this is where usually your question is, last point. But before going to the last point, we need to cover the other points and proper understanding is needed. Okay. Right. So this is not a new slide. This is something we have already discussed. Storage is hierarchical. On top, you have the registries, which is part of your processor or ALU. So below that, you have cache memory. Very specifically, we have the L1, L2, and L3. Then your main memory or the RAM. This is what we are really interested here. Then you have the secondary storage, SSD or hard disk, and tertiary storage, that is external hard disk, CD, pen drives, and so on. And of course, the ROM is also there, keeping the firmware, which can be loaded to memory and taken to the processor. And memory and above are volatile. Secondary, tertiary, and the ROM is non-volatile. That is, even when you switch off the machine or discontinue the power supply, main power supply, these contents retains. And when it goes up, the speed and cost goes up, but the capacity goes down. That is fine because for processing you don't need a lot of capacity. So right. So this is more specifically, we have subdivided the cache memory also into L1, L2, and L3. And typically L1 and L2 cache is in the CPU or the processor itself. This is a multi-processor environment. And L3 cache is in your motherboard, close to the RAM. Okay. So therefore, when your processor need to access some particular content from memory. Of course, remember the memory has both programs and data. Your processor will never directly come to the RAM. It first check whether that particular content is in the L1 cache, which is in the process side. If it is there, it will get it from the L1 cache. If it is not there in the L1 cache, we say cache miss, L1 cache miss, then it will check the L2 cache. If it is there in the L2 cache, it will take it. Then we say it's L2 cache hit. If L2 cache also miss, it will check whether the content is in the L3 cache. If it is not there, that means L3 also miss, then only it will look at it, go to the RAM and take it. But whenever you take it from RAM to the registries, you put it into the L1 cache again. L1 cache එක පින්නකොට ඒවා L2 එකට යනවා. L3 එකට යනවා. ගොඩක් අලුත් මේවා තියෙන L1 එකේ. පරණ ඒවා තියෙනවා L3 එකේ. සමහර ලාට L3 එකනොත් ගිහිල්ලා. එතකොට cache එකේ නැහැ. පරණ වෙන cache එකෙන් අයින් වෙනවා. මොකද ඉඩ ගන්නවා. So that is how it works. So you must know that cache is a hierarchy. L1, L2, L3. And first it look at in the L1, then L2, then L3. If it is not found in any of these, only get it from the RAM. And whenever you get it from RAM, you put it into the cache. So that next time you have a higher possibility of getting that same data. So then someone will ask, how do you know that there's a higher possibility of accessing the old data? Because if you are in a loop or something, if you are in a method, so those local variables and those things, there's a higher chance that you will again and again need it. That is why we keep it in the registry, cache, both data and instructions. Okay. So any questions up to this point?
So, what if the required data is not in the RAM as well?
So, can you give me an example? For example, say you are running a program. Okay. So if you are running a program, first thing is that program is loaded to the RAM. Okay. For example, say now you are running Photoshop. Let's assume that Photoshop, when you install, it is about 2 GB. Okay. So therefore, when you start Photoshop, part of the Photoshop is loaded to the RAM. Maybe about 300 megabyte of program code. Okay. And also now you are editing a particular photo, JPEG file. So when you are editing a particular image, usually that image is also in the RAM. Okay. So therefore, most of the time your program, the essential part of the program is in the RAM and your data is in the RAM. But again, there's a possibility, say you are now doing some photo editing, but you are now using a particular feature, which is sort of a rarely used feature. So therefore, that part of the program is not loaded to the RAM. So in that kind of a situation, what happens is the operating system load that part of the program also to the RAM. Right? If your RAM has free space, if the RAM doesn't have free space, enough free space, it will take part of the RAM, which is related to some inactive program, and put it into the secondary storage or virtual memory and take some space to take this part to the RAM. Now it is in the RAM. So therefore, now you can execute that particular feature. So that happens in the background. We can't see it, but that happens. And the other thing is, say you have loaded a video and you are watching that video. Say that video is about 1 GB, maybe movie, 2-hour movie. And again, the entire movie is not loaded to the memory because then maybe about 2 GB is taken up by the movie, and also that is not productive. So then only maybe for the 5 minutes or 10 minutes buffer is loaded to the memory, and gradually in the background it will keep loading the next 5 minutes, and so on. So therefore, your answer for your question, If it is not in the RAM, that means it has to take that to the RAM and then access it, because your processor never ever directly access secondary storage. Right? It never ever directly access your hard disk or SSD. So therefore, everything your microprocessor access, data or programs, first it must come to the RAM and then access from the RAM. So when your RAM is running out, it can take some of the part of that to the secondary storage to take that space. Or when you are closing the programs also, you are releasing the RAM, right? For example, if you have a lot of RAM, usually it is not an issue, right? For example, now in my case, I have only 8 GB RAM, which is very modest, okay? Very modest. You can see that out of 8 GB, already about 6.80, very close to 7 GB is used. So only about less than 1 GB is free, right? So if I start another program, okay, so let me start another program, something like, okay, something like this. So you will see that the memory goes up because now that program, part of that program is also loaded to the memory. So you can see, but again, you can see that, yes, it goes up, but sometimes it comes down also. So the reason is, while it takes some more memory, in the background, it is putting some other inactive programs memory to the virtual memory or the secondary storage. Okay. So therefore, after some time, this will again go down a bit. Okay, go down. You can see now it's going down because it is in the background taking some inactive programs memory to the secondary storage. It tried to survive with 8 GB as much as possible. But my computer is getting slower and slower because it has to do this swapping frequently. And of course, when I close programs, definitely it is going to release some memory. You can see all of a sudden. So therefore, your operating system somehow manage with the existing memory with the help of virtual memory as well. So if your content is not in the memory, maybe part of your big Word document, sometimes when you keep scrolling, sometimes you might feel like it hangs. So usually when you are scrolling a Word document, very smoothly you can scroll. But if I scroll too fast, sometimes it hangs. That means the entire document is not in the memory. Maybe it has loaded 10 pages. Now you want to quickly scroll to the 100th page. And now in the background, it is taken to the memory. So therefore, if your processor need to access something, first of all, it must be loaded to the memory. Okay, so otherwise, it will never ever directly access from your secondary storage. I hope that answered your question. Okay.
So then what
Yes.
about that inactive program which has been moved to the secondary storage? What happens to it after the program that we selected is closed?
Can you repeat that question? Yes, inactive programs can be taken to the secondary storage to take the memory. Yes. What is the second part of your question?
I just wanted to ask what happens to the program that we run after after the program we selected is closed, what happened to the that inactive program which has been transferred to the
Okay.
secondary storage?
Okay, right.
Is
So
it
yeah,
uh,
now I got the question. Right. So now remember inactive programs, part of the memory or the entire memory is put it into the virtual memory or the secondary disk because of we are running out of memory. Now maybe we close our program, other active program, or it has terminated, or it has now fully run. Now operating system in the background again take those inactive because it knows that we have memory, right? So it's playing that game, but there's no guarantee. Maybe there are so many inactive programs and we have limited memory. So therefore, some of the inactive programs will be taken to the memory, right? Maybe that inactive program is still in the memory. But the moment we give attention, for example, you can see that in my taskbar, there are so many inactive For example, I have not given attention to the WhatsApp for a very long time. So there's a high possibility that the memory related to WhatsApp is in the secondary storage, because my operating system can't guess what I'm going to do next. So therefore, probably WhatsApp memory related to WhatsApp may be in the secondary storage. But the moment I give the attention, it immediately load it to the memory, because because that is why it happens in a very small time, within few milliseconds. Okay, but there are situations when you give attention, it take time to get the window. So that means now the programs are getting slower, because there are so many programs competing for the memory. Now, of course, the operating system need to write something to the secondary storage and free the memory, and then get that virtual memory related to that program back to the memory. So that is why sometimes when you give attention, sometimes it will not immediately come. So that is good. But there are slow machines. When I give attention to a window, it takes sometimes 5 seconds to look, see the window. So that means it is in the background taking that virtual memory to the memory, and to free it first, it has to write something back to the virtual memory, and then take it back, and then it is getting executed. So that is why when your computer is slow, there are two reasons. One reason is your processor is not fast enough. Second reason is your RAM is not enough. So if you have always a lot of free RAM, right, about 3, 4, 5 GB is free RAM, so that means it doesn't need to do this memory swapping frequently, right? So, but if you are running out of RAM, it needs to frequently access the secondary storage. Okay, so that is how it happens. Okay, so therefore, when you close a program, maybe an inactive program's memory comes back to the main memory, or still it is in the secondary storage. But when you give attention, definitely it needs to come to the main memory. Sometimes it might take a little bit of time. Sometimes it can happen very quickly, depending on your performance of your computer. Okay, right. So that is how it works. So has it answered your question?
Yes, sir.
Okay. Right. Right. So how do you look at the memory? So we know that in compute, everything is set of ones and zeros. Everything, right? Set of ones and zeros at hardware level. So therefore, you can think of the memory as sort of we have memory locations. Each memory location, maybe you can keep 1 byte or maybe 4 byte, depends on, and each location has an address. Maybe this is my 000 address, maybe 1 byte of data, see, set of ones and zeros, 8 bits. Maybe next memory address, next memory address, next memory address, and each memory address you can keep, assume 1 byte of data. Sometimes it is 1 byte, sometimes it is 4 byte, it depends. Okay. So that is why you have 32-bit, 64-bit, and operating systems also. So this is how you look at it. Your memory address is a binary number. Your content is a binary number. Right? And your content can be related to data, like Word document, image, audio, video, or memory locations. Set of memory locations are keeping data related, the content related to programs like Word, Microsoft Word, and so on. Because your program instructions are set of zeros and ones at binary level. Okay. And each memory cell is a flip-flop. Remember, we discussed about what is latch, right? So flip-flop is little bit of advanced latch, more reliable latch. So therefore, each memory cell is a latch or flip-flop. So therefore, each memory cell can retain or remember whether it's 0 or 1. And at any time, you can set it to 1, reset it to 0. And anytime you can read the value. And if it is 8-bit memory location, so you have 8 latches for that memory address. Okay, for that memory address. So that is how you look at the memory. Of course, that is the correct picture. So you have the address, you have the data. Most of the time, addresses are referred as hexadecimal numbers, but in reality, hardware level, it's a binary number. Okay. So memory address translation is our main topic. So that topic is all about how to get this address. Because there are two type of addresses called the physical address and logical address. So I'm referring to the physical address, physical memory address. And this is your data or the content. Data means programs and data. Okay. Or contents. So the better word is memory address, memory content. Okay. So you can visualize it as this. So then I already mentioned you about the virtual memory. Virtual memory is you borrow part of your secondary storage as an extension to your main memory, but actually it is not memory. So therefore, don't think that your memory is actual memory is 4 GB and you have virtual memory another 2 GB. Therefore, your actual memory is 6 GB. 6 GB. No, your actual memory is still 4 GB. But your operating system look at it as something like 6 GB. But it doesn't mean that it can directly access the other 2 GB in the virtual memory because you need to do swapping and then access it. Okay. So that is called virtual memory. And if you go to the task manager, settings, and if you search for something called maybe virtual memory, no, you can search for something like environmental variables, system environmental variables. There you have, performance tab. There's another setting. You can see virtual effects, processors, scheduling, memory usage, and virtual memory. If you go to the settings, you can see more details about virtual memory. Go to the advanced. So you can see virtual memory. A paging file is an area on the hard disk that Windows uses as if it were RAM. You can look at the English terms which they use. A paging file, it's a file uh, in an area of the hard disk. Of course, in my case, it is not hard disk, it's SSD. Still, the Windows, they are using the old terminology. Users as if it were RAM. ඒක RAM වගේ කියලා හිතාගෙන එයා පාවිච්චි කරනවා. So in my case, it has been allocated 15,360 megabyte. Okay, so that is about 10 GB. Okay, 10 GB because 1024 megabyte is 1 GB. This is not 1025, this is about 15,000. So that means about 15 GB is allocated for virtual. It doesn't mean that always it use 15 GB, maybe just using 1 or 2 GB, but it has allocated dynamically. So that is called what? Virtual memory. Virtual means not real. Not really the memory, but your operating system can think of it as part of the memory. So therefore, you have the real memory, that is your hardware memory. In my case, it's about 4 GB, 8 GB. And of course, it can take maybe another, say, let's assume another 4 GB as virtual memory. And your operating system consider that this entire thing as the memory, but it doesn't mean that this can be directly used. So physical memory, virtual memory, and all together we can call it logical memory. Logical memory. So that is the preferred terminology. Physical memory, virtual memory, and all together we can call it logical memory. But unfortunately, some people call virtual memory also as logical memory. So therefore, a lot of confusions are there because this wording is not standard. But in our discussion, I will be using three terms: physical memory, virtual memory, logical memory. But sometimes in your examiner, refer to the logical memory also as virtual memory. Okay. So therefore, be cautious about the terminology, because some people use these words in a different context. And when your main memory or the physical memory, you are running out of physical memory, you can write part of this physical memory to the virtual memory, so that you can load another program or another data. And later that part you can again take back to the physical memory by freeing up some resources. Because when you're running, accessing, your processor must always access the physical memory and not the virtual memory. So therefore, there's a swapping of pages from physical memory to the virtual memory and virtual memory to the physical memory. So swapping. Okay. It happens at page level, set of bytes, set of megabytes actually. Pages are taken to this, and maybe that page is taken back to the physical memory. Right. Any questions about that? So that is called memory swapping, going from physical memory to the virtual memory or secondary storage. And secondary storage in the sense not as saving to the your hard disk as a file. It's a memory dump. All the content of this memory page is written. It is different from saving your file. Right? Saving a file is not memory swapping. Right? So this is just swapping memory. Right. So our final subtopic is memory address translation. So now we have covered all the concept related to memory. Other than this, and this is a little bit bigger topic, and this is the critical topic for your exam, because almost every other year there's a question from on memory translation, because examiner knows that a lot of students are very poor in doing these kind of calculations, and without understanding what is virtual memory, what is page, what memory page, right, you can't understand this calculation as well. So therefore, we will take this memory address translation next time. So that means next time we have about 1 hour session. Then we can do some past paper questions. Okay, so next class we will not start a new topic. Rather, we will do some past papers after finishing the memory address translation. Okay. So again, just go through the note before the next class and see whether you can understand at least some part of it, uh, so that in the class you can do it, you can understand it and ask, clarify things. So when you, before coming to the class, when you read the note, the advantage is you have specific questions, which you need to just clarify and understand during the session. Otherwise, what happens is when you get into the class as a blank, without looking at the note, so sometimes you don't understand certain part and you don't know which part you have understood, which part you don't understand. But when you read the note and come, you have specific objectives, targets. I want to understand these things which are still gray. Okay. So therefore read the note and come. Of course, this is little bit difficult part to understand directly, but anyway, read the note and come. Okay. Right. So we'll stop at this point. Right. Thank you.